Today's material is about related rates problems, which are really just word problems involving taking derivatives. Usually derivatives with respect to time, so everything is going to be changing as time moves on. Okay, when we did the chain rule in class, our first example was about a weather balloon inflating, and the radius was growing at 3 times time, so after 1 minute the radius was 3 feet or something like that. And then we also had this formula for volume of a sphere because it was a spherical weather balloon. We wanted to find how fast the volume was changing with respect to time, right, the rate of change of volume with respect to time. And we found that using the chain rule. So there's the chain rule. Here's a different way to approach it. This uses implicit differentiation, which really is the chain rule by another name. Okay. Our volume formula gives a relationship between the quantity volume and the quantity radius. But both of those quantities are in fact functions of time. That is, at different points in time, volume is different, and at different points in time, radius is different. So both of these are functions of time. So I can take their derivatives with respect to time. So we're going to differentiate that whole equation with respect to time, d over dt of that whole equation. When we do that, the derivative of volume is just dv dt, and on the right we use implicit differentiation, 4/3 pi times 3r squared times dr dt. Again, that's just the chain rule or implicit differentiation, however you want to think of it. But notice that this equation gives a relationship between rates of change, the derivative of volume with respect to time and the derivative of radius with respect to time. So this gives a relationship between the rates of change of the quantities in the original equation. We can simplify, and we see that again we still have the chain rule here. This thing, 4 pi r squared, is the derivative of volume with respect to radius. So this is just the chain rule again, in disguise. But I'm thinking of it as starting with a relationship between volume and radius, and then taking derivatives gives me a relationship between the rates of change of volume and radius. In this particular problem, then we would have substituted in 3 and so on, but that's what we did in class, and I'm not going to worry about the details of that particular problem. The idea, though, is to solve a related rates problem, you use a relationship between quantities, like volume and radius, and you use implicit differentiation, and you come up with a relationship between rates of change. Thus, related rates, relationships between rates. There are a few steps that are useful. You don't have to follow this step by step, but I think it can be helpful. Usually you want to draw a diagram, write down rate information, figure out an equation, differentiate that equation implicitly, and substitute in. So a little more detail. You draw a picture of the situation. It's usually a word problem. Often there's physical things that you can draw pictures of. And you want to label quantities in your picture. So if a quantity is changing with time, like the radius or volume in the previous example, you give it a variable name, v, r, etc. If a quantity is constant, it's not changing at all in the course of the problem, then you just put a number there. You don't need a variable. Now you figure out of all those variables you wrote down, which rates of change, which derivatives do you have information about, and which rates or derivatives are the ones you're looking for. You write an equation that relates all the quantities in your diagram. So sometimes this is an equation that comes from geometry, like a formula for volume. Sometimes it's other information in the problem that lets you write an equation down. And then you implicitly differentiate that thing with respect to time. So you're taking d dt of a bunch of stuff, and since you're doing this implicitly, any variable in the equation will end up with its derivative after you do implicit differentiation. So if you had a v, you'll end up with a dv dt in your equation. If you had an r, you'll end up with a dr dt. If you had an x, a dx dt. Maybe you had height, so you'll have a dh dt, and so on. Then you want to substitute into that new equation, the one that you got by taking derivatives, all the information that you had in step 2 about the derivatives you were given. You substitute that in. Sometimes you also need to substitute in information specific to a particular moment in time that the question is asking about. and then you can solve for the unknown rate. Here's an example. I have a snowball, it's melting, and it's melting at a rate of 1 square centimeter per minute. So that's its surface area changing. I would like to know how fast its diameter is changing at the moment in time when the diameter is 8 centimeters. So the snowball is changing size, right? Sometimes its diameter starts off bigger than 8 centimeters, and then it shrinks, and then eventually it gets smaller than 8 centimeters and perhaps disappears entirely if it melts long enough. But I want to know how fast that diameter is shrinking at the moment in time when the snowball has a diameter of 8 centimeters. Okay, I need to draw a diagram. There's a snowball. Its diameter, you are tempted to label it with an 8, but resist that temptation. It is only an 8 centimeter diameter at one particular moment in time. The diameter is changing as the snowball melts. Over the course of the problem, the diameter is changing, so we don't get to label it with a number. We have to label it with a letter. Now, you can label it D for diameter, but I personally prefer not to label things D, because then when I take derivatives, I've got something like d dt, and it's just a pain. So I'll call it an X for diameter. Also involved in this problem is the surface area. That's a little harder to label in the picture, so I just wrote it down. A is going to be my surface area. I need to write down rate stuff, so the derivative of A and the derivative of X with respect to time. I'm told that surface area is decreasing at 1 centimeter squared per minute. So that's a rate of change of surface area, so that's dA dt. That tells me dA dt is negative 1 square centimeters per minute. The negative is because it's decreasing, right? It is changing in the negative direction, so my rate of change is negative. dx dt is the rate of change of diameter, and that's what I'm looking for. In fact, I'm looking to find out what dx dt is at the moment in time when x equals 8. I need an equation that relates the quantities in my problem. In this case, that's going to be the formula for the surface area of a sphere. The surface area of a sphere is 4 pi times the radius squared. I don't have a radius in my problem, I have a diameter, so radius is x over 2. And therefore, I can simplify and get that the surface area is pi times the diameter squared. That's my equation. It relates the quantities in the problem. Surface area equals pi times diameter squared. Now I need to differentiate implicitly with respect to time. I'm going to take the whole equation and differentiate both sides with respect to time. On the left, I just get the derivative of area with respect to time, and on the right, pi times 2x, or 2 pi x, times the derivative of x, 2 pi x dx dt. Now I substitute in what I know. I know that dA dt is negative 1, that's over in step 2. And I also know that I'm interested at the moment of time when x equals 8. So I can put in negative 1 for dA dt and 8 for x. And that's what I get. And notice that dx dt is the only thing there that I didn't substitute for, and that's because it's what I want to find. I rearrange and I get negative 1 over 16 pi. That's great, but it's a word problem, so I should involve some units. And the units of a derivative are always the units of the top over the units of the bottom. So units of x over units of t. In this case, that's centimeters and minutes. Therefore, I can say that the diameter is decreasing, right? Notice that the rate of change is negative, so it's decreasing at 1 over 16 pi centimeters per minute. There's the answer. We will do many more of these in class, as many as we can get to. But for your video question, let's say I was doing a problem and step 1 looked like this. That is, I drew a diagram and the two legs of this right triangle are changing, but the hypotenuse is always 10. So I've labeled it like so. Skip step 2, which is rate information. I'm not telling you the setup of the problem, so you don't know that. But do step 3. Step 3, remember, is write an equation relating the quantities. So do that, turn it in class, and I'll see you there.